Are you able to see my screen? Is is my screen visible to you?
Yes.
Okay, thank you. Uh, Hello everyone. My name is Ria, and today I'll be presenting our work on advancing subgrid scale turbulence modeling through a Liutex based modification of the WALE model. This is a joint work with Dr. Yufi, Mariam Sangi, Krishna, and Dr. Chao Kwan Liu uh, at University of Texas Arlington. Let's begin with the agenda. Today's agenda. Uh, Here's the roadmap for today. We'll start with turbulence modeling challenges, then review DNS and LES basics. We'll look at the Smolkinski and WALE models, identifying WALE's limitation and introducing Liutex theory. Finally, I'll show how Liutex modifies WALE and present the validation results. Uh, let's start with the motivation why turbulence modeling is so difficult. Turbulence is chaotic and multi-scale, and it heritedly unresolved. Even with modern computation, predicting turbulence remains one of the hardest problems in fluid mechanics. The DNS, which is direct numerical simulation, resolves all scales but is prohibitively expensive. LES, which is large eddy simulation, offers a practical alternative. It resolves the large eddies and models the smaller ones. To appreciate LES, let's first recall what DNS actually solves. DNS solves the full time dependent Navier-Stokes equation. The governing equation is this, where ui is the velocity component in direction I, t is the time, xj represents the spatial coordinate in direction j, p is the pressure, rho is density, nu is kinematic viscosity, and delta is the Laplacian operator. DNS provides instantaneous 3D flow fields with the higher fidelity, but the cost grows as Reynolds number increases. Since DNS is impractical, we turn to LES, which filters the equations. Now that we have seen DNS, let's talk about turbulence and context of like LES. Turbulence is made up of a swirling structure called eddies. This eddies uh, are the building blocks of turbulence, and they come in a wide range of sizes. The larger the eddies contain most of the energy, while the smaller ones are dissipated by viscosity. Viscosity, as we all know, is the fluid's resistance to deformation. And when we talk about vortices, we mean regions of rotating flow around an axis. LES, which is large eddy simulation, is designed to resolve the large eddies directly while modeling the smaller scales that we cannot afford to compute. This makes LES a practical alternative to DNS. One of the earliest approaches to modeling this small scales was a Smolkinski model introduced in 1963, and we'll look in Smolkinski model in details. It was the first subgrid scale model for LES. It approximates the effect of unresolved turbulence by introducing an eddy viscosity. The equation is this one, where nu is the subgrid scale viscosity representing the small effect of eddies. Cs is the Smolkinski constant. Delta is the filter width, which is usually related to the grid size. And this is the magnitude of the strain rate tensor, which measures how the fluid elements deform. This model is simple, robust, but it has limitation. Near wall, it produces error. It tends to add excessive dissipation, which damps out important structures, and the constant used here is not universal. To address these shortcomings, Nicode and Ducros propose the whale model, which adapts viscosity more intelligently. Let's look into the whale model. It adapts eddy viscosity to local flow condition. It vanishes in pure shear. It supports laminar to turbulent transition and has correct near wall scaling. The formulation for whale is as provided, where this is the whale constant. The delta is the filter width. Sij is the strain rate tensor. SDIJ is the traceless symmetric part of the velocity gradient tensor. This model is invariant to coordinate transformation and requires only local information. The limit Now we'll see the properties of whale model. Like as I said, it vanishes in pure shear flow, supports laminar to turbulent transition. It is correct near wall. It invariants to coordinate transition and rotation and requires only local information which is suitable for complex geometrics. But whale do have limitations, which is whale's expression is not very simple to compute and it does not reflect the correct angular velocity. To overcome this, we introduce the Liutex theory. Liutex is a mathematical rigorous vortex identification vector. It separates rigid body rotation from shear and stretching. It provides both the vortex axis and rotational strength. The Liutex vector is defined as this, where R is the Liutex magnitude and this R is the eigenvector of velocity gradient tensor. Omega is the vorticity vector and lambda ci is the imaginary part of complex eigenvalue. Like representing the swirling strength. Now let's see how we used the Liutex to modify whale. Uh, In Liutex whale model, we replace whale's numerator with the Liutex magnitude. The denominator remains unchanged. This is the formula that we used, where CR is the Liutex whale constant and R is the Liutex magnitude. Other terms are as defined in other terms are the same as it was defined in the whale. This retains near wall scaling, distinguishes shear from rotation, and suppresses viscosity in vortex cores. Uh, let's look into the results. Like this was the result where this is the DNS and this yellow line is the proposed, that is Liutex based whale. It does perform better than the no model and simple Liutex. This is the isosurface structure. In the beginning, we can see the small circular things and this is at the end. This is the whole surface structure in 3D. And this is the result for Reynolds stress, which is for U prime V prime. This is for U prime W prime. The blue is the DNS and the orange highlighted part is the modified whale. This is the graph which represent Reynolds stress for V prime V prime. And this is for V prime W prime. As we can see, like this is for DNS and this is for modified whale. This is for W prime W prime. And this is the skin friction where this is the DNS and the black one represents the proposed method, which is the modified whale method. Uh, In summary, the summary for the whale model: LES filtering of Neostrock equation, eddy viscosity approximation for CGC stresses, zero viscosity in laminar shear, uh, local physically consistent formulation suitable for complex flows. It partially distinguishes rotation from shear, but not perfectly. The summary for Liutex based whale model is uh, it is zero in pure shear and irrotational regions, non-zero only when rigid body rotation exists. It provides unambiguous vortex strength measures, no wall damping required. It detects only rigid body rotation, not simple shear, improves discrimination between shear and rotation, and enhances preservation of coherent structures. To conclude, whale is effective and robust, but not explicitly use the correct rotation strength, where Liutex based whale incorporates a mathematically rigorous vortex vector, and Liutex based whale preserves coherent vortex structures and improves LES. This is the references of the papers that was used. This is my contact information. Thank you.